Welcome back to tutorial 6, where we're going to be extending our model to turn it into a radiative convective equilibrium model. To recap our last tutorial, you converted your zero-dimensional model that told you about global mean surface air temperature into a one-dimensional model that told you about how that temperature varied with height, which is our dimension. But it didn't work as well as we hoped at predicting the observed global temperature structure of the atmosphere, which is what's shown on the left panel here. So we're going to be adding another element of physics to this model that will hopefully make it better reproduce the observed temperature structure of the atmosphere. And to understand that physical process that we're adding, we're going to ask the question of what happens if you warm air at the surface. So if you take your initial air parcel at the surface, represented by this blue dot, and you gave it some heat because it was over some particularly warm land or ocean. And so it moves to where this red air parcel is because its temperature increases. So far we've assumed that the only way heat gets moved into or out of the Earth's system or between different layers of the atmosphere is via radiation, the emission and absorption of radiation. But if we were to warm an air parcel at the surface, we know that the ideal gas law says that its properties will change. In particular, its density, which is inversely proportional to temperature, will decrease if the temperature increases. And obviously if the density decreases enough, that air parcel will want to rise into the air above like a balloon would. And in that case where the density of a surface air parcel decreases enough that it wants to rise into the denser air above, then we say it becomes buoyant and it moves upwards. And so this movement is actually a very important process for moving heat around vertically in the atmosphere. And we're going to talk about that a little bit more in a second. But to understand how we can use a plot like the one on the right to tell whether an air parcel is going to move upwards or not, so whether it's buoyant or not, we're going to have to recap the idea of lapse rates, which we encountered on day 1 of this week. And the lapse rate was something that told us how the temperature of an air parcel would change if it were lifted up in the atmosphere adiabatically, which means without exchanging heat with its surroundings. And we know that as we move up in the atmosphere, the pressure decreases, and as a result, the temperature of those air parcels also decreases as they get moved upwards. And that decrease is something that we can plot on these skew T-plots like the one on the left. So for that particular surface air parcel, the blue air parcel, then we can plot its lapse rate, and what that line represents is the temperature that air parcel would have if we were to move it up adiabatically in the atmosphere. And so if we moved it up, it would follow that line as it moves upwards. Now, that surface air parcel, the blue one that we started with initially, has a lapse rate that lies to the left of the observed temperature profile above that parcel. And what that means is if we move that air parcel upwards, it would be cooler and denser than its surroundings. And so it will want to sink back to the surface. And in that case, we say that the air is stable or it's not buoyant. But if we look at the warmed surface air parcel, that red dot, then its lapse rate is shifted to the right and actually lies to the right of the observed temperature above. And in that case, if we move the air parcel upwards, it would be warmer and lighter than its surroundings. So it would want to continue moving upwards and be buoyant. And so that's how we can use these types of plots to tell whether or not an air parcel is buoyant or not. And this process of surface air warming and moving upwards in the atmosphere due to its buoyancy is a very important process for redistributing heat vertically in the atmosphere. As that air rises, it takes the heat that it's gained at the surface upwards and it mixes with the air around, distributing that heat throughout the layers above. And this process is called convection, and you've probably seen it regularly in your everyday life. For example, this cumulonimbus cloud in the photo on the right is caused by convection, where surface air parcels get warm, rise rapidly, and as they rise, they cool, and water vapor within those air parcels condenses out to create clouds like this. And those air parcels can rise for kilometers into the atmosphere, creating deep clouds like this one. Unfortunately, we can add this mixing, redistribution of heat to our models that we've been using so far today, this one-dimensional model that you made in the last tutorial. And when we do that, it turns into a radiative convective equilibrium model, or an RCE model. And so you can look at what this RCE model predicts for the surface and vertical structure of the atmosphere in this next tutorial.